Hi, welcome to CodeCrucks. In this video, we will talk about the another version of finite automata, that is non-deterministic finite automata. We will understand first that what is determinism and what is non-determinism, and we will differentiate DFA and NFA through example. Then we'll formally define the NFA. We'll see how to represent the NFA, and at the end we will talk about extended transition function for the NFA. So as we have learned in previous videos, the DFA's transition function has exactly one transition for each state symbol pair. That is, if we are given some state Q and if we read some input alphabet A from that, then the transition can go to one stage only. So that may be a self state or it may go to another state P. The transition function for the diagram shown in this figure is given by delta Q comma A is equal to P, because on reading symbol A from state Q, it is going to state P. So here transition is fixed, but in case of NFA, we can have 0, 1 or more transition for state symbol pair. As we can see in the diagram, from state Q, if we read input alphabet A, then we can move to state P1, state P2 or some state Pk. That means here we are moving to set of states instead of single state as in DFA. And the transition function for this can be defined as delta Q comma A is equal to set of all the states P1, P2 up to Pk, where we can move by reading A from state Q. Let us see some example. First we'll draw DFA for the language, and for the same language we will derive NFA. Let us consider the language L, which is set of all the strings W over alphabet A comma B, such that the string W contains the substring double A. That means the language contains all the string over AB such that there must be double A present into the string. So if we start with the smallest string, that would be double A, then length of string 3 would be A double A, B double A and double AB. Then length of string 4, that would be double A double A, then it would be triple AB, B triple A and B double AB, and so on. So there would be infinite such strings. The only condition is that every string must contain double A as a substring of it. Let us draw DFA for this. So Q0 is the initial state. To reach to the final state, we must have to read double A. So if we read first A, we are moving to some state Q1, which is non-final state, because A is not acceptable. When we read second A from Q1, it moves to final state Q2, because we have already read out double A from the Q0. But this DFA only reads double A. We have to produce DFA which reads all the strings which are having double A as a substring. So now we will be introducing various arcs on it. We have to test all the input alphabet arcs from all the states. So right now we have two inputs A and B. So from each state, we will try to adjust the arc of A and B. Already I have explained that whenever we generate the arcs, we should look for the smallest possible arc. So first we'll look for the self loop. If it is a valid, keep it. If it is not valid, then check for the next neighbor, either on left or on right. Whatever arc is feasible, add it. If that is not feasible, check for the next to next neighbor and go in that way. So try to establish smallest arc, then larger one, then even larger than that, etc. So that we can generate maximum possible strings. So from state Q0, there is no arc for B. So if we put self loop of B, then is it possible all the strings generated by that contains double A? Yes, definitely. Fine, we can read double A, we can have a B double A, we can have a double B double A, triple B double A. So all strings are valid. So this arc is also valid. From state Q1, if we put arc of B as a self loop, then we can also create a string A, B, A, and we might be in final state, which is not a valid string because A, B, A is not valid. So we cannot put self loop of B on Q1. Fine. So now we will look for the next neighbors, that is Q0 or Q2. Similarly, if we put arc from Q1 to Q2 for input alphabet B, then we can read A, B string as well. From Q0 we will read A and we will move to Q1. From Q1 we read B and we will move to Q2. So string AB is accepted, which is not valid. So we cannot put arc of B from Q1 to Q2. So the only option is to check whether it is possible to set from Q1 to Q0 or not. So if we put arc of B here, then as we can see that to go to the final state, we must have to read AA. Then only we can go to the final state. So if we first read B, then A, then again B, then we'll come back to Q0. Then to go to the Q2, we must have to read double A. So this arc is valid because all the strings generated by this must have double A. From Q2, we have to generate both the arcs. So if we put arc of A as a self loop, then it is valid because double A is already there into the string, and that is why we are in Q2. Right? And similarly, we can put self loop of B as well. So this would be the transition diagram for the language which is mentioned here. So this is how gradually we can build up the DFA. Let us trace the string. Suppose we are in initial state Q0 and we are given some string A, B, double A, and we have to check whether DFA will accept this string or not. So input is A and state is Q0. So if we look at the transition diagram, we are moving to state Q1 on input A. So one symbol is processed, we are in state Q1 and remaining symbols are B double A. So from state Q1 we have to read B, so we are moving back to state Q0 and remaining string is double A. From Q0 we have to read A, we are moving to Q1, input alphabet is A. From Q1 if we read A, we are moving to state Q2, entire string is processed, we are in Q2 and Q2 is final state and hence this string will be accepted. Let us now try to simulate this with NFA. So we'll derive NFA for the same string, and as we know that in NFA we can have multiple branches or multiple arcs for same input from same state. So first we'll derive the NFA for the smallest possible string, that is double A, and now we will try to adjust the link, but now our task is easier because we don't have to worry about the multiple arcs from the same state. So I can simply fix A and B here. So whatever strings are produced, they will definitely have a double A in it. So we will be reading any number of A and B and we will be moving to either Q0 or Q1 and then Q2. And similarly, we can read any number of A and B after reading double A. So this is totally valid. So this is NFA because from state Q0, if we read A, we remain on a same state and we can move to the Q1 as well. So there are two transitions for single input from state Q0. Hence it is NFA. Let us now try to simulate the same string with this NFA. In state Q0, input is A. So there are two possibilities. Either it will go to state Q1 or it will remain in state Q0. In both the case, remaining string is now B double A. From Q1, there is no transition for input alphabet B. So this string will be rejected. That means this path is not valid. So we have to backtrack and follow the next branch. Now we will check from Q0. Is there any transition for B? Yes, it is. We will remain on the same state Q0. From Q0, input alphabet is A. So again, there are two possibilities. Either it will stay on same state Q0 or it will move to the state Q1. From Q0, if we read input alphabet A, then we will remain on same state Q0 or we can move to the state Q1. In either case, now entire string has been processed. Let us check whether these are the valid states or not. So Q0 is not final state and entire string is read out. So reject this path. Backtrack, go to another branch Q1 comma epsilon. So Q1 is also not a final state, so reject it. Now move to the next branch, that is Q1 comma A. From Q1, if we read A, then we are moving to state Q2 and entire string is processed. And as Q2 is a final state, this path is valid path. So as we can see that in case of NFA, the movement is not linear. Rather, we have to do a lot of backtracking to confirm whether string is a member of language or not. So the process of recognizing string is slower in NFA because it might has to move through multiple paths, but in NFA it is quicker. But the advantage is that construction of NFA is quite faster compared to DFA. Look at the formal definition of NFA. NFA is defined by 5 tuples, capital Q, sigma, delta, Q0, capital F, where capital Q represents set of states into the NFA. Sigma is a set of all alphabets, input alphabets. Delta is a transition function. So delta is the one which will differentiate NFA in DFA. In DFA, we have seen that the transition function was from Q cross input alphabet to Q. That means we are in some state Q and we are reading some input alphabet from sigma, then we are moving to one state in Q. Only single state. Whereas in case of NFA, the output could be any subset of states. So ultimately it can be any set from the power set of the state Q. So the transition function would be from Q cross sigma to 2 power Q. 2 power Q is nothing but it's a power set. If you have any difficulty in understanding power set, I have already prepared the video. You can find the link in description box. Because we can move to no state on reading input in NFA, or we can move to one state, we can move to 2 states, we can move to 3 states. So there would be 2 power n number of possibilities. So that is what the power set. Q0 is the initial state and capital F represents the final state, which would be subset of the original set of states Q. So the definition is almost the same to DFA, only difference is in transition function. Let us represent NFA. So consider the language in which strings are ending in A. So the smallest possible string would be A. Then strings of length 2 would be double A and BA. Strings of length 3 would be double AA, ABA, BAA and double BA. And string of length 4 would be 4A and etc. Okay, this is an infinite language. Now for this, we will design the transition diagram. So Q0 is the initial state. If we read A, then we are moving to final state because A is a valid string as we can see in language L. But this NFA or DFA represents only one string, that is A. We have to make sure that it reads all the possible strings which are ending in A only. So now we will check for the possible arcs from Q0 and Q1. So from Q0, if we read A and B, then we will remain in Q0, and to move to the final state, we must have to read A. That means definitely string will end with A. So this is valid representation. The another representation of NFA is using transition table, where in rows we are putting states, in column we are putting input alphabets, and in intersection of those two, we will be writing the states on which transitions are happening. That is from state Q0, if we read A, then we are moving to state Q0 and Q1. So in case of DFA, it was only single state, but in case of NFA, it is a set of states. So typically we write it within the curly bracket because it is a set. Similarly, from Q0, if we read B, we are moving to state Q0 only. And from Q1, there is no transition, so that will be phi or the null set. That is the another representation. Formal definition, we have already seen that NFA is defined by phi tuple Q, sigma, delta, Q0, F. And as we can see from the transition diagram, capital Q is 2 states, Q0 and Q1. Then input alphabet sigma is A comma B. The transition function delta, that is defined by the transition table. The initial state is Q0 itself and final state is Q1. And the transition function is like this. That is defined by delta is equal to Q cross sigma to power set of Q. And we have 4 possibilities: Q0A, Q0B, Q1A, Q1B. And appropriate transitions are shown onto the right hand side. So we can represent NFA either using transition diagram, transition table, or transition function with the formal definition. The extended transition function delta cap. So normal transition function is represented by delta, which is defined over one alphabet. So we are in some state Q, and if we read a single symbol A, then where we are moving? So we may be moving on set of states P1, P2 up to Pk because it is a NFA. And the extended transition function is defined over string instead of alphabet. Fine. So delta cap is represented by some state Q. And if we read string W now, instead of a single symbol A, now we have to read string W. Then what will be the possible outcome? So that will be again set of states. Let us call it as a R1, R2, Rk. So extended transition function holds true, and that we will prove by induction. So the base case is that delta cap Q comma epsilon would be Q itself, because epsilon means we are not reading any symbol. So if we are on state Q, if we do not consume any input symbol, then obviously we will remain on to the same state. Okay, there will not be any movement. So this basis case would be delta cap Q comma epsilon is equal to Q. Induction stage would be, we will represent our W, that is a string that may be of 2 symbol, 3 symbol or n symbols. We are decomposing it and we are writing into the two form. Initially we have a string of n minus 1 symbol, that is X. And finally we will concatenate it with the last symbol, that is A. Fine. So X concatenation with A forms W, where X is a string and A is a symbol. So the transition function, extended transition function on W can be defined as delta hat Q comma W is equal to transition function delta of delta hat Q comma X comma A, because the transition function is defined over string. And we know that W is represented by X concatenation with A. So this part will be extended transition function, and A is an input symbol. So we can apply the normal transition function or standard transition function on that, and we can rewrite it like this. Now we know that when we apply the transition function delta Q comma A, the output is some set of states P1, P2 up to Pk. So we can drop this transition function and we can replace the output as P1, P2 up to Pk. And if we repeat the process for all this P1, P2 up to Pk states, then we will get the desired set of states R1, R2, Rk. So when we take the union of all the states for input symbols A, then union of them will give us the final output state. So this will be doing the recursively. So we can say that ultimately finally delta cap Q comma W will be R1, R2 up to Rk. Example of extended transition function. Let us consider string L as a language L is a strings ending with 10, and we have to check whether string 1010 is accepted by NFA or not. So first we'll derive the NFA for that. So Q0 is a strings ending in 10. So this is the smallest possible string. Now we will check for the arc. So from Q0, arc of 1 is already out. We have to check for the arc of 0. Can we have self loop? Yes, definitely we can have a self loop, right? And even we can have a 0 and 1 because it is a NFA. So we can definitely put it like this. All the strings in DFA would be ending with 10. Now let us trace whether extended function holds for this or not. Let us consider the string W is equal to 1010. And from the base case on the previous slide, the delta cap Q0 comma epsilon will be Q0 itself, because we are not moving to any state if we do not read anything in normal NFA. Now we will read the first symbol. W is 1010, first symbol is 1. So gradually we will be proceeding one by one symbols. So first we'll read the first symbol, that is delta cap Q01. This is our W right now. We can write down it as a X comma A. So X will be epsilon and A would be 1. So that we can write down delta of delta hat Q0 comma epsilon comma 1. Because see, this is our W now and we have to represent it as a X dot A. X is n minus 1 symbols and A is the last symbol. So as there is only one symbol, our X would be epsilon and A would be 1. So from the previous slide, we can represent or we can write the function as like this, delta hat Q0 comma epsilon 1. But from the previous step, we know that delta cap Q0 epsilon is Q0 because there is no input symbol and so we will remain on same state. So this part will reduce as Q0 only. So we have now delta Q0 comma 1, and if we look at the diagram, then this is a normal transition function. So if we read input 1 from state Q0, then we are moving to state Q0 and Q1. So that is the output of delta hat Q0 comma 1. Now we will consume the second symbol. So that is delta hat Q0 comma 10. So now this is a string. When we write as a x dot a, x would be 1, a would be 0. Right? So this is represented like delta into delta cap Q0 comma x. X is 1 comma a is 0 from the previous slide. And the output of this we have already computed in previous line, which is Q0 comma Q1. So that will be replaced by the set Q0 comma Q1. And if we take the transition on this for input 0, then that will be union of transitions from Q0 to 0 and Q1 to 0. So that is delta Q0 comma 0 union delta Q1 comma 0. And from the transition diagram on left, it will give us Q0 comma Q2. Let us read the third symbol Q01. Okay. So Q101. So again, if we write it as a x dot a, then 1 would be a and 10 will be our x. Okay. We always have to write down this w as a x dot a, where x is a string and a is the last symbol. So we can write it as a delta hat Q0 comma x, that is 10 comma a, that is 1. This part we have already calculated in previous line, that is Q0 comma Q2, and this can be written as a union of Q0 comma 1 and Q2 comma 1, and from diagram that will result into Q0 comma Q1. And finally the entire string 1010. So a x dot a, if we compare this with that, then x would be 101 and a would be the last symbol 0, and that we can represent it like this: delta cap Q0 comma x, that is 101 comma a, that is 0. And this part is already computed in previous line, that is Q0 comma Q1, and the transition from Q0 to on Q0 Q1 for input symbol 0 would be union of these two, and that is ultimately Q0 Q2. So we have processed entire string, and we have to check whether 1010 is accepted by NFA or not. So when it returns some set of states R1, R2 up to Rk, if any of the state is a final state, then we can say string is accepted. So whatever states we have derived here, we need to take intersection of that with the final state, which is Q2, as can be seen in the diagram. And the intersection is not null, it is some state Q2. So definitely, as this belongs to set of final states, W is accepted. Fine. So if we follow some different path, we might go to the Q0. So that state will reject the string. But if we follow some different path, we can go to the state Q2, and that path will accept the string. So this is how extended transition function works for the string in NFA. Let us consider NFA n, that is standard 5-tuple representation. Then language of this NFA n is given by all the strings W, such that if we apply the extended transition function on W from state Q0, then we will get some output as a set of state, and if the intersection of that with final set of final states is not null, okay? It means whatever states are represented by transition function on W, it must contain final state, then only the string is accepted, otherwise it is not. So collection of all such strings will form the language of NFA. Thank you. That's it for today, folks. See you in next video. If you think this video was useful to you, then please like, comment and share. Don't forget to subscribe the channel CodeCrucks. Press the bell icon for the notification of latest videos. Stay connected, stay tuned. Thanks for watching. Bye-bye.